Meta Artificial Intelligence is presenting attention mechanism with an example. At the heart of the transformer model lies the attention mechanism, a pivotal innovation designed to address the fundamental challenge of learning long-range dependencies within sequence transduction tasks. The attention mechanism revolutionizes this learning process by dramatically reducing the distance between any two positions in the input and output sequences. As described by Vaswani and colleagues in their seminal 2017 paper, Attention is All You Need, this mechanism allows the model to focus on the most relevant parts of the input sequence when generating each element of the output sequence. The attention mechanism operates on the principle of mapping a query alongside a series of key-value pairs to produce an output, where each component is represented as a vector. This architecture enables the model to compute the output as a weighted sum of the input values, with the weights themselves being determined through a compatibility function between the query and each key, as shown in the equation below and in the original attention architecture on the right. Let's simplify the concepts of queries, keys, and values in the attention mechanism with a straightforward example. Imagine you're reading a book and come across the sentence, "The cat sat on the mat." We want to understand the importance of sat in this context. This might be representing the word sat if we're trying to understand how sat relates to other words in the sentence. The query is essentially asking what is relevant to sat in this sentence. Queries reflect our quest for knowledge. Keys could be all the other words in the sentence or certain features of these words that help to identify their role or relationship to the word sat. Each word acts as a key that the attention mechanism will use to determine how relevant it is to the query. For example, cat and mat would be keys. In a straightforward application, the values could also be the words themselves or some representation of them that provides more context about the sentence. The value associated with each key provides the content that we care about once we've decided which keys are relevant to our query. Let's put some numbers and calculate the attention for our example. First, we have embeddings for a small vocabulary consisting only of the words in our sentence. Each one is represented by a different 2D vector. As we focus on the word sat, Q for sat is given by the vector 1, 1, focusing on action-related context. As mentioned, keys are like tags for every word, indicating how relevant they might be to your focus. In our sentence, each word will have a key suggesting its relation to the concept of sitting. For simplicity, let's assume the vectors k and q are the same. The second action to take is to calculate the dot product scores between q and k, where our query for focusing on sat is 1, 1. The third operation is scaling of the resulting dot product by the square root of the dimensionality of the key vectors, in our example d equals 2. It is done to prevent extremely large values in the dot product, which can lead to gradients that are too small for effective learning. The fourth operation is the Softmax activation function, aims to convert the result into a probability distribution. In our case, these are the attention weights that sum up to 1. It indicates the relative importance of each word in the sentence with respect to the query, sat. Finally, the last operation is computed as a weighted sum of the value vectors, v, where the weights are the attention scores from the Softmax step. The final output vector for sat is 0.7, 0.5. This vector is a weighted representation of the word sat in the context of the sentence, focusing more on itself and the word cat. This process demonstrates how the attention mechanism can dynamically emphasize certain parts of the input based on their relevance, allowing models to capture nuanced relationships in the data. In real-world applications, these calculations involve high-dimensional vectors and are performed for every word in the sequence, enabling the model to understand complex dependencies in a given context. In practical applications, the attention function is applied to a collection of queries at once, which are consolidated into a single matrix Q. Similarly, keys and values are grouped into matrices K and V, respectively. Let's present the multi-head attention. This method innovates beyond the traditional attention mechanism, which utilizes keys, values, and queries of a uniform model dimension. Multi-head attention diverges by projecting these elements into different dimensions multiple times through unique, learned linear projections. This isn't merely an expansion but a deliberate strategy to diversify attention across various dimensions. The benefits of multi-head attention are profound. It allows the model to simultaneously focus on distinct representation subspaces and positions, offering a comprehensive view of the information. It concatenates multiple heads of Q, K, and V. Traditional single-head attention mechanisms might average out critical nuances, but multi-head attention maintains and emphasizes these distinctions. Equations 3 and 4 below represents the concatenations of multi-head attentions together. Thanks for watching.